Now, even though it's not going to be on the test, we went ahead and did a graph of a rational function. Okay? Now, this function was originally just shown as you see it. Zeros at -5 and -1, vertical asymptotes at x equals -3 and x equals 2. So, your numerator is what gives you the zeros at -5 and -1. Both of these zeros appear to be, not necessarily, but appear to be linear, plausibly linear, so that the numerator is going to contain x plus 5 and x plus 1, so you get zeros at -5 and -1. Asymptotes occur when the denominator is 0. Vertical asymptotes occur when the denominator is 0. Okay, the denominator is 0 at x equals -3 and x equals 2. So the denominator is going to contain factors of x plus 3 and x minus 2. Now you can see that at the asymptote, vertical asymptote at x equals 2, the function is positive on one side, negative on another. That's like the 1 over x function. So this is acting like a transformed 1 over x function, a horizontally shifted and vertically stretched 1 over x function near x equals -2. Meaning that the function, the 0 of the denominator here is going to have multiplicity 1. Now it could have multiplicity 3 or 5, an odd multiplicity. We're going to assume multiplicity 1. Okay, here at x equals -3, this thing acts like the reciprocal square function, doesn't it? It's positive on both sides of the asymptote. Okay, now it could be negative on both sides of the asymptote, and you'd still draw the same conclusion. So it doesn't matter whether it's positive or negative, but if it's on the same side of the asymptote, that means you have in the vicinity of that asymptote a horizontally shifted reciprocal square or reciprocal even power function. And we'll keep it simple. We'll assume it's a reciprocal square. So there it is. Okay, that 0 occurs, that 0 of the denominator has to occur for an even power that we'll assume is 2. Okay, so there we get zeros of the denominator at x equals -3 and x equals -2 and x equals 2. And the denominator has zeros there. So you have vertical asymptotes. Now there's a little more to being sure that these are really vertical asymptotes. You'd have to be sure that the numerator doesn't share any of these, either of these zeros. Things get more complicated, but we're keeping it simple for right now. Okay, so it's going to be some multiple of this numerator divided by this denominator is going to give us a function that looks very much like this. Okay. We want to evaluate A. Treat it just like we did previously. We plug in 0 for all these numbers, and we notice that our vertical intercept, our y-axis intercept, is at y equals -8. So you're going to set -8 equal to A times what you get when you plug in zeros. Now we could say that as f of 0 is -8. F of x is A times this. So f of 0 is -8, and f of 0 is 0 plus 5, 0 plus 1, 0 plus 3, 0 minus 2 squared with the A, just this expression we have here. Well, evaluate this, and this is pretty easy to evaluate. I'd be embarrassed if I didn't get it right. Not that embarrassed. So this comes out, numerator comes out 5, denominator comes out -6, it's -5/6 times A, and that's equal to the -8, so we multiply A by 6/5. Okay, A is 6/5 of 8. Actually, -6/5 of -8, but that's the same as 6/5 of 8. It's 48/5 or 9.6, so we conclude that our model might well be 9.6 times the quantity x plus 5 times x plus 1 over x plus 3 quantity squared times x minus 2. Now there's one little wrinkle in this, and this isn't actually going to be accurate. So I intentionally drew something that looks like a slant asymptote here. Okay, that slant asymptote implies that the degree of the numerator is 1 greater than the degree of the denominator, and that isn't the case. It's the degree of the denominator is 1 greater than the degree of the numerator. So this might not even be a possible shape of such a function. If it was this function, in fact, the value of the function for large absolute values of x would have to approach 0, because the degree of the denominator is greater than the degree of the numerator. Just think about what happens if x is huge. The square of a huge number times a huge number divided into a huge number times a huge number is the reciprocal of a huge number. So if I wanted to actually have the graph of this function, it would have to, could come down here, but it would have to approach 0. And this one could come down here, but it would have to turn around and approach 0 here. You'd have to have a horizontal asymptote for large values of x. Another way of saying it is, overall, this acts like 9.6 times 1 over x. In other words, your basic 1 over x function, like this, and like this, okay, multiplied by 9.6, but modified in this region by the fact of your zeros of the numerator and zeros of the denominator. So there's more to say about rational functions, which is one reason that I cut the test off at polynomials. Rational functions can be a little more complicated, and we'll get to that next week, actually later this week.